This week is just going to be about monads specifically, because they're really important, but they're also more abstract, and they take a little time to get used to. And then I think next week we'll do modalities. I guess people will probably be most interested in that part, and Jake will be back, and maybe that's why there are less people today. I don't know. But okay, so monads are this nice, elegant, categorical way of describing algebraic structures. Contrasted with Levere theories, they're very Levere theories spell everything out very explicitly, but monads are kind of the opposite, and they say everything in like the sleekest way possible. So, so the classic example, so monads come from these dualities called adjunctions or adjoint functors, if you've ever heard of those. And the basic idea of these adjoints is that when you have two categories and functors between them, and the categories themselves are already one-dimensional objects. They have morphism information in them already. Then it's too strong to talk about isomorphism for two things for one map. So if you've never heard of isomorphism, that means when you go there and then come back, you get exactly where you started. And the idea is that since these are already one-dimensional objects, we need to weaken our notions of what it means to be like an inverse to something else. And so like two categories are equivalent if you go there and come back and you're not exactly where you started, but you're somewhere isomorphic to where you started. So you have your whole category, you send it over and come back, and the image could have shifted some, but it's essentially the same. But there's a very important weakening of that, where instead of it being that notion of an inverse, we have kind of the closest thing to an inverse when one doesn't actually exist. And so it's called adjunction. And it's kind of like an irreducible unit of difference. And the classic examples arise from when you are adding like some little unit of structure or removing some unit of structure. So the classic examples are when you have the category of sets on one side. Is this specific? You just have plain old sets on one side, and then on the other side you have some simple algebraic structure. So like we were talking about last time, if you have like a set of three elements over here, you can take the free monoid on that set, and that corresponds to the monoid of all lists of elements that use the symbols from your set. And that's the free monoid, because the idea of being like a free algebraic structure is about when you make something into a certain structure without imposing any unnecessary relations or doing anything more than you need to. So the only thing about a monoid is that it has an identity, and then it is associative. And so lists do that in like the easiest, simplest way possible. So you just use the elements of your set like symbols, don't impose any relations between them. And then you just make all possible lists using those symbols. And so like the empty list becomes the identity of the monoid. And then you include the single elements as kind of generators of the list, of all the possible lists. And then from there, just all possible concatenations of those. And so this is the idea of taking a free monoid. And then to go back, all you do is take the underlying set. You just forget that it's a monoid and just turn it back into a set. So this, I should write it like that, where this is a set paired with an operation, and you're just forgetting to go back. You're just forgetting about the operation, which seems kind of silly, but yeah, one of these directions is doing more something more interesting than the other. But the point is, when you get back to set, going there and coming back is an endo functor, which means just a functor going from a category to itself. But it's a special kind of endo functor that it now has this ability to multiply with itself, and that is like encoding the binary operation that you got from this functor, except now you're like in a single category and the object can communicate with itself. So that was pretty vague, but let me do an example. So a monad is it has a multiplication and a unit such that certain diagrams commute. So you have
sorry, Christian.
Essentially associativity of this is an example of times in category theory where it gets very circular and self-referential, because a monad, you might have heard the quote that a monad is a monoid in the category of endofunctors. So between any two categories, you have a whole category of functors between them. And like we've been talking about with Levere theories, you have the theory of a monoid, and then you can like map it into any category. So a monad is literally like a monoid in the category of endofunctors. But because people are scared of math, they use that quote to act like they're really complicated. But hopefully this example is going to help. So this is saying associative, and then we have unital, just like last time. But now they mean something different because we're kind of on a level of abstraction here. Now it's not. It's encoding the associativity and the unitality in kind of a so same thing as last time. If we like adjoin this unit and we do Tn and then multiply, or eta t and then multiply, it's like doing nothing. So so this is being a unit, So the point is showing y'all what this actually means for lists. So the idea is that this multiplication is like a more abstract version of the same operation that you had when you were doing the free monoid. And then this one is kind of like inclusion of generators. So in this case, we're thinking about lists. So in this case, so one is denoting the identity endofunctor. So it's taking some set ABC and including it into the set of all lists of using ABC, but just including A, B, and C as the singleton lists, which literally generate all of the other lists by concatenation. And then similarly for multiplication, it's going to take a list of lists. So that's what this taking powers of the monad is going to correspond to taking lists of lists of lists of lists. So what is a reasonable guess for what is taking a list of lists and creating a list? It's just going to be flattening it out and making it, just collapsing it, concatenating all at once and making it one big list. So instead of a binary operation, it's kind of just doing like everything it's loaded up at once. And so you have a list of lists here. And it's just going to collapse them all at once. And so now what these axioms are saying is that here, if you have a list of lists of lists, it's interesting. It's kind of like saying associativity on a higher level. You can either collapse the inner two first and then the outer two, and that's going one side, or you can collapse the outer two first and then the inner two. Does that make sense?
So Christian,
yeah, so it's interesting. It's just like saying associativity on a higher level.
Hey Christian, can you hear me?
Yeah.
Hey, so is this similar to so what am I trying to say here? So we start with some set like ABC, right? Like three elements or something. We form that free monoid, so like the free language on those generators. And then it's like to go to T2, then it's like we're doing the free monoid on the free monoid at that point. And then to go back to T, we're just collapsing that. We're basically applying like the forgetful functor at that point, right?
Yeah.
Okay.
Yeah. I didn't want to get too deep into the thing about adjunctions, but there's a clever way that this multiplication works that uses kind of the opposite side. I could draw it real quick just so you know what's going on in the anatomy of this.
That would be really cool.
Yeah. So if you've ever taken an abstract algebra class, there's this diagram about free groups that they talk about. Where they say, given some set X and the free group on that set, they usually forget to specify this, the underlying set, because they need to be of the same type. Then any other time that you try to put a group structure on that set, it's that kind of addition of structure is going to factor through that free group. And the idea is like, if you've ever heard of presenting a group by generators and relations, then that's what this is doing, is that the free group has no relations, and you just do the groupiest possible thing with your set. And then here, the unique factorization is modding by whatever relations you need to quotient by, which means just like identifying things that need to be identified. And then this right here is the unit. This this thing that is factoring everything, that is the actual unit of the monad. So it's from the identity on your category to iterating there and back once. And then kind of the dual diagram is happening on the other side. So here you have the free group on the underlying set of a group. This side's a little harder to think about, but it's just the opposite thing. And it's called a co-unit. And it's part of something called a co-monad. Monads are about algebra and putting things together. Co-monads are about so-called co-algebra. And there's a whole really interesting side of computer science that's all about co-algebra, because it ends up making more like spatial objects as opposed to algebraic. And they do like labeled transition systems that that describe operational semantics of that's a subject for another time, because what Greg and Mike are actually doing with Ladle and these enriched Levier theories is actually a totally different approach than what is the generally accepted like consensus in the computer science community right now as to how to approach operational semantics. And the other approach, it's like really similar, but they haven't explored the connections yet. But that's a topic for another time. But anyways, here, it's just like the opposite thing happening. And the way that you do the multiplication of the monad, so here, like the co-unit is doing the opposite, where you have going there and coming back, and you are able to collapse that to the identity. And so the point is, when you have t squared, which is UF, then you use the co-unit on the middle to collapse that to the identity, and then it goes back down to this is what is. It's interesting the way that like this duality kind of like is interpenetrating itself. And so here we use the co-unit on the middle, and this collapses to the identity, and then you're left with, so you keep the U the same, and then the co-unit, and then the F the same. It goes back down to UF. And this is what does the operation, whatever it may be. So in this case, it's collapsing lists. That's the basic idea. Any questions about that? Okay, so the monad itself is not the object you're actually interested in, but you want to think about all of the algebras of a monad. So in the same way that the theory is just kind of the abstract form, and what you really care about are the models of the theory, there's actually a direct correspondence and these really nice theorems where each Levier theory generates a monad, and there's an equivalence not only between those, but between the category of models of the theory and the category of algebras of the monad. So now we're going to say what these algebras are, and then hopefully get to a general idea of why these things are equivalent. So, and we still haven't really talked about like how you actually get a monad from a Levier theory. And so the idea, let's talk about algebras first. So given, let's say you have a monad T on set, then an algebra is just some set A equipped with a morphism, or in this case, it's just a function, from its monad image back to itself. And the idea is that this function is just some operation that is compatible with how the monad works. And so that being compatible is going to be equivalent to saying that this is some operation that is associative and unital. So the monad itself was kind of the free way of doing that. And then anything compatible with it is going to be just associativity and unitality in general. So here it's some function such that here you can either multiply the monad on one side and then keep the A the same and then do the operation. You can either multiply with the monad and do the operation, or here you can keep one of the monads the same and do the operation and then do the operation again. It's kind of this thing in category theory where you start to get familiar with this idea where being compatible is just like any time where there's two different structures going on and there's kind of two possible paths that you could do, those two orders that you could do those operations or whatever they are, then they should be equal in order to be compatible. So this one is saying that if you have a list of lists of stuff in A, you can either collapse the list first on this side. And the idea is that this beta is just some operation. It could be just like adding up everything in the list or something. It's just any operation on a list of things that is going to be associative, and that's what's making it compatible here. So either you can collapse the list first and then do the operation. So let's say you're just adding them up, or you can do the operation first in each of the lists. And so this is a list of lists, and so separately for every list you add everything up, so you get a set of sums, and then you do it again and add up everything left. I could have made the notation less ambiguous, but hopefully that makes sense. Okay. So you see this is equivalent to saying that the operation is associative. And it's just cool how the monad kind of says it more powerfully than the way we usually say it, with like one parentheses at a time, and then you recognize like, oh, you could build up all possible reparenthesizations. So that's the idea. And then similarly, you have to be compatible with the unit. So you have some TA. Wait, what am I doing? You have just some set, and you make a list out of it via the unit, and then collapse it back down. Then that's like doing nothing. So here you I shouldn't have chosen A. Let's see. So you have some X here. Am I doing this right? So here, this includes it as a list, just a singleton list, and you collapse it. It's like doing nothing. But no, sorry, it's saying more than that. Let's see. You have some list. Oh, yeah. You have a list. Yeah, it's just like the way it looks for. Yeah. So you have some list here, X, Y, Z, and there's two kind of silly things you can do with it. You can either make it a list of lists like this, where you're, this corresponds to post-composing with the unit. So once you do the monad once, what it thinks of as singletons are just single lists, and then you make that just a single list of lists. Or first you do the unit, so it includes them as singletons first. Is that visible? And then either way, you collapse it back and it's like doing nothing. So in a weird way, this is using the empty list as the unit. I'm not sure how to say that, but yeah. Questions about that? So now,
can I ask about this first equation? TA to
sorry, hold on.
A.
I can't hear you.
Oh, oh sorry.
Okay. Yeah.
Do you hear me?
Mm-hmm. Yes.
So I want to ask you about this first equation, the TA beta to A. Why didn't you write T square A? Yeah, no, about this first equation, not about the unit, but yeah. Why you didn't write T square A beta to TA? Or A is just one list, right? And TA is list of lists. Or
yeah. So A is just a set, and then this is lists that use that set.
Oh, A is a set.
Yeah, sorry. Yeah, probably should have chosen X or something. Yeah. So this is some operation on lists that's compatible with how lists concatenate, and yeah. So this is just like think about adding up everything in the list, for example.
Okay, thanks.
Yeah. Mm-hmm. Yeah. So this is the idea, is that anytime you have a monad, you get a whole category of algebras of the monad. And in this case, it's kind of funny because we get back to where we started, where we had an adjunction between sets and monoids that made a monad, and then the category of algebras of that monad just ends up being equivalent to one of the sides of the adjunction in the first place. So when we think about the category of algebras of this free monoid, it's just the category of monoids, because we saw that was equivalent. And so these are these special kind of dualities or adjunctions called monadic adjunctions. And they're weird because it seems like one of the sides already knew about the adjunction, because it like was the category of algebras over the monad that the adjunction induces. So it's a strange thing, but all of these free forgetful adjunctions are like this. And it's interesting because Levier theories, the correspondence between Levier theories and monads kind of clarifies or kind of dissects how that's happening. So now we're kind of going to get a finer grained view of this duality, and then see why every Levier theory gives you a monad. So that's one of the big points about Ladle, is that we want to make whatever theories we need very explicitly, but then package them up really nicely as these monads, and then that allows us to define distributive laws between them. So given any theory, you get an adjunction between, so let's say you have some theory like the theory of monoids. And so y'all are probably tired of seeing this drawn by now, but you get this in the usual diagrams, etc. And then you map all of this over, and you're thinking about all the ways that this can be modeled in just sets. So, there's a whole category of models, the functor category, from this category back to set, and you denote it like this. So from the theory back to set, and remember, we only want to think about functors that preserve products, because everything in our theory is dependent upon, or is defined by products. So this is the category of models where the objects are functors, and then the morphisms are natural transformations between those. So remember, a natural transformation between two functors is going to take, so let's say, for example, you had, let's see, some model, model 1 is going to consist of a bunch of in-area operations. So this is like this underlying set of the monoid, and then you have a bunch of operations, and then you have some other model, and it's not just, let's see. So we're mapping this theory two ways on the same set, two different ways of putting a monoid structure on one set. Then the natural transformation paints one of them onto the other. And it doesn't just do this for a single set, but it just, like, every time that for every x, it's doing this. It's going to it's going to paint the image of one of the models onto the other. So this is just about why this is a category. Being compatible like this is saying you can either do the operation first for the first monoid and then map over, or map over two things first and then do that operation. And you see that's exactly saying being a monoid homomorphism. The definition of a homomorphism in algebra is just that you can either do an operation first and then map over, or map the things over and then do the operation. So we can see that in the case where this is the theory of monoids, then the category of models back in the set is just the same thing as the category of monoids. So in the same way that we saw that the monad, when you thought about its algebras, it ends up just being monoids like we had from the very beginning, then this is the same idea. So anytime, any questions about that?
So you're just saying that this comes down to the fact that the natural transformations have to be monoid homomorphisms, right?
Yeah.
Okay.
Yeah.
Cool.
They, in this case, they're literally functions, or the components of the natural transformation are functions, but because of the way we've constructed everything with that square, it's precisely just like a more refined way of describing a monoid homomorphism. Yeah. So the point is that given any Liouville theory, there's a duality between set and the category of its models in set. So there's an adjunction here, and it's just going to be a more refined view of what we started out with, just doing the free monoid, but not really knowing what a monoid is. Now we've dissected it and made it into this nice theory and pointed out that it's this category of models. And so now, now the main thing is, what's this nicer theory way of saying what a free model is, rather than just a free monoid? And then the underlying one is still going to be pretty simple. So the free model on a set is basically, you need to package up all of the operations that you could do on the set without imposing any relations. So here, you're going to send it to this is where it gets a little more complicated. But here, remember that the objects are functors. So we're taking some object, but then we're going to send it to a functor that is now waiting itself for an object of t. So it's going to wait for some n, because remember the objects are natural numbers representing the powers of the, sometimes we write it like t to the n, but it might get kind of confusing, so we'll just write n. And then we need to get a set, and that should just be the set of all n-ary operations on our set x. So this is going to be the set of all f of x1 to xn, where f is one of the n-ary operations in our theory, and these xi are in x. So it's all of these guys, such that f is one of the n-ary operations, and these xi are elements of x. So this is how we take some set and package up all of the n-ary, just all of the operations that you could do on that set. Does this make sense?
And the set on the left is like it's a language that you use to transform it to the right side, right?
Mm-hmm.
It's
Yeah.
operation on the set on the left.
Mm-hmm. Yeah.
And this n is element of t.
Yeah.
Okay. Thanks.
Mm-hmm. Yeah. So there's nicer categorical ways of saying this, and you kind of need them in order to show that this is a monad, and it gets kind of complicated, but we just need the general idea, and then given some functor, some model like this, how any guesses of what we do exactly to that functor to get the underlying set? So remember this each of these functors, because it's product preserving, it's kind of determined by where it sends one, right? So we're just picking out like the carrier of the algebra, and then the rest of the functor is just like powers of that one generating object. So that one carrier just corresponds to the underlying thing. So here we have some model, let's call it M. Where's the eraser? We have some model M, and we're going to send it to its value at 1. we're just going to evaluate it at 1. So remember, this was sending each n to some x to the n, and we just want that x. We just want the carrier, the underlying set of the. Does this make sense?
Are we using the same what Daniel mentioned for the product in the category, which we always have in the category for this? Okay.
Yeah. Same meaning of product. Okay. So this is basically a more refined view of what it means to take the free algebra and then take the underlying set. And the point is now there's this nice way of describing what the monad is. So when you go there and come back, you get this T, and what is this going to do to a set? It's T of X is going to be basically you just get all of the n-ary operations together by a so-called coproduct. So maybe I guess we haven't gone over that yet, but in sets it's just disjoint union of sets. It has the opposite universal property as the product. So in the product, you're taking all pairs and you're kind of like maximally interrelating things, but with coproducts and least ordered way. And so for sets, it's just disjoint union of things. So they don't even know about intersection. It's just kind of the least ordered way to put things together. So in this case, so it's drawn with kind of the upside down product symbol, and then here you take these pairs of n-ary operations times the nth product of your set, and you're going to go over all natural numbers. So we bag up all of the n-ary operations for all n, but then we need to do a little more, because in the structure of the category, there's tons of ways that operations can factor through each other, and there's tons of different orders that you could do things, and you need to make those all equivalent. So you need to mod by those relations. So the basic idea is that the monad is just taking some set and then making all valid terms of the theory up to equality in that theory. So first it generates all of the possible terms, but then because of the structure of your theory and it as a Cartesian category, certain things should be made equal, and so you have to just equate all of those. So the idea is that this monad is just assigning to every set all of the terms of the free theory on that set, or the free model of that set up to equality of the theory. So yeah, it's kind of a little hard to explain, but does this make sense?
So for the coproduct, you said we can kind of think of a disjoint union, or is that the wrong thing?
Yeah, no, it's literally just the disjoint union.
It is literally a disjoint union. Okay.
Yeah.
All right.
Yeah.
Perfect.
Mm-hmm.
This is like a sum type in programming.
Yeah, exactly.
I have questions about the monad. In programming, I understand monad through mostly through bind operation or join. But you are not talking about bind, right? You're talking about the join operation which collapse structure.
Yes. Yeah. You're talking about like a join of lists, or
Join, like if you have lists of lists, you get lists, and this is the join.
Yeah, the join is the multiplication of the monad. Yeah, I'm pretty sure.
Multiplication in which sense? If you have a list of lists, you get a list.
Mm-hmm. Yeah, yeah. So the multiplication that we were talking about before. I think in general for any monad in computer science, that the join would correspond to that.
Oh, okay. So yeah, so this is like a binary operation between two lists, or I'm not seeing this as a binary operation. If I have a list of lists.
Yeah, it's not exactly a binary operation, because that list of lists could be infinitely long. That's the weird thing about monads, is that it's kind of on a higher level of abstraction, where the squared just refers to being a list of lists and not the number of things it's taking in.
So this is operation between inner lists.
Yep.
If I have a list, I'm doing like a monad operation on inner lists.
Yeah.
Between inner lists. Oh, okay. Okay, thanks.
Mm-hmm. Yeah. Yeah. So we get this monad, and from my really rough explanation that I should think about how to say better. It's all of the terms, valid terms of the theory, in the same way that when you take the underlying set of the free monoid on some set, it's just all of the lists of the theory. So that's something to not overthink. And so that's the basic idea. And so the thing is that now we can define distributive laws. That's the main reason we want to think about monads instead of Liouville theories, and programmers like monads better. But so when we talk about, so the reason it's called a distributive law is because there was some category theorist / algebraist that was interested in formalizing the distributive law of a ring, just the classic example that we're used to of multiplication literally distributing over addition. They wanted to formalize that and really generalize that in a big way using category theory. And so he found this really nice thing where, so does anybody not know what a ring is? Something from algebra. So it's just kind of generalizing the integers. So where you have two operations called like plus and times, and the plus forms an abelian group or commutative group. So it's a lot better than a monoid because you also have inverses, so like negative numbers, but you also have commutative, so that you can, like a plus b equals b plus a. And then under the times, I should be writing this down, the times is just a monoid. So using our knowledge of theories now, we could say that a ring is literally a monoid in the category of abelian groups. And then you get the crucial effect that the monoid multiplication needs to distribute over the addition. So a ring is some set R plus times such that R plus is an abelian group, which means just what I said, and then R times is a monoid, such that the multiplication distributes over the addition. So such that for all ABC, A times B plus C equals AB A times B plus A times C. And then similarly for the other side, A plus B times C equals A times C plus B times C. Okay, so we deal with these a lot in math, and fields are like nicer rings, and that's where you start getting into manifolds and everything. But just plain old algebra is mainly about rings. So anyways, this distributive law, we're like massively generalizing it. And so here, we were talking about the fact that we could literally think of this as mapping the theory of monoids into the category of abelian groups. So you just have some abelian group structure, and then you're also putting a monoid over it. And because of the way the functor works, you do get a distributive law. Then there's this nice way of formalizing that phenomenon where you have one monad on set for the free abelian group. So in this case, it's a little harder to describe because instead of just being lists, you need to also have negative elements, and it needs to be commutative. So they become unordered lists, and you have to, for every element of your set, you also have an inverse element, and you just formally adjoin like something that you denote as an inverse. And then we also have our free monoid monad like we've been talking about. And then this distributive law, the idea is that it's literally a natural transformation from the multiplication of the monoid and the addition of the abelian group. It's a natural transformation from that composition to the addition of the abelian group over the multiplication of the monoid. So here, like this, you can think about this as all of the expressions where you have some plus, which came from composing the monoid, and then some times outside. And then you're literally just transforming it in this nice coherent way to the sum of times. So this is why we call it a distributive law. Questions about that? So we're just making a huge generalization of this in an important way, where now we want to think about terms of collections, which is some formula that was built up from multiplying certain collections together to being a collection of terms, which kind of distributes out the different rules in all the possible ways to get the collection of terms that satisfy that formula. So it's quite a leap from here to there, but we've built up all the theory that that we can understand this. So that's probably where I'll stop for today. But if anybody has questions.
Is it ring always this combination of abelian group and monoid, or?
Yeah.
Oh, it's always okay. We had this assignment from Greg to make Arabic numerals with the plus. So
oh yeah.
This is something that it's not completely the same, but it's similar. But plus and adding digits, is this like a form or a ring, or I'm not sure.
So if you don't have negatives, then if you only have the positive numbers, then you're just a monoid. So the classic example of a monoid is the natural numbers. But once you add the negative numbers, the integers are a classic example of a ring.
And if you don't have integers, but you have digits that you must combine, but we didn't have this distributive law between combining digits and the plus, so it's not completely the same. Probably.
What do you mean by combining digits?
You only have generator for your language are only digits, so you must combine digits to get another digit. This is like a monoidal operation, but the plus is also monoidal here. So we have two monoids.
Yeah.
But they're not ring, because.
Yeah. Yeah. It probably has some other name, but yeah.
Oh, okay.
There's tons of different algebraic structures. Yeah.
Cool.
Okay. Well, yeah, that's it for today.
Oh, this was excellent. Thanks.
Yeah.
Yeah. Thank you so much.
Yeah, you're welcome.
Awesome. See you guys.
All right. Bye.
See you. Bye-bye.